This is lecture 19 in BBSP 610. We'll be continuing our discussion of regression, particularly performing statistical inference and other forms of hypothesis testing using regression. That as we discussed in the previous lecture, using regression you can predict the value of a response variable y based on a predictor variable x. We may want to know how confident we are in our regression estimates. In particular, is the association between x and y real? Is it a stronger association than we would expect to observe due to chance? If it's real, how strong is this association? How confident are we in our predictions of y? So say we want to test the null hypothesis that there's no association between x and y, and in most cases this is equivalent to testing the null hypothesis that the slope of the regression line is 0. In other words, you can write h0 as b1 is equal to 0, or b1 is the slope of the regression line, and the alternative hypothesis that b1 is not equal to 0. And a little theory on this, it doesn't matter if you don't understand this 100%, I'm just laying it out there. I'll explain how you can do this in practice in a minute, but it's the same type of theory that we had when we were doing inferences about a sample mean, that when we wanted to do inferences about means, we assumed there's some sort of unknown and unobservable population mean that we would try to approximate using a sample mean, and we would try to quantify the amount of uncertainty in the estimate of the sample mean. We can do something analogous for regression. The idea is that there's some true unobservable regression line, yi equals b0 plus b1 xi plus epsilon I. Epsilon I is just a noise term to account for the unexplained variability in the model. And we approximate it with the sample regression line where the regression coefficients are calculated using least squares regression, as I discussed in the previous lecture. And it turns out that you can show that the expected value of the regression line is b1. That is, if we took a bunch of samples, we took a bunch of different samples from the population, calculated regression lines for each of those samples, and took the average over time, the average regression coefficient would approach the true value of the regression coefficient. And the standard error for beta 1, or for b1, is given by this expression on this slide, which is complicated. You don't have to worry about it. I'm never going to ask you to calculate it. R will do it for you. But if you ever need it for some inexplicable reason, there's the formula. And if we know the expected value and standard error of a regression coefficient, then under the null hypothesis that b1 is equal to 0, then b1 hat divided by the standard error of b1 hat will have a t-distribution with n minus 2 degrees of freedom, implying that we can get a 95% confidence interval for the regression coefficients by taking b1 hat plus or minus the standard error times the appropriate quantile of a t-distribution. So let's go back to the cars example that we've used in the past few lectures. If you'll recall from the scatter plot, there was some pretty strong evidence that stopping distance increases as speed increases, and we want to know if this association is statistically significant. That is the pattern closer to a straight line than we would expect to observe due to chance, or more formally, can we reject the null hypothesis that the slope of the regression line is equal to 0? Well, in R, if you use the summary command in R, it'll automatically perform this test for you. If I create cars.lm the way I did in the previous lecture, and then I say summary cars.lm, then you'll see two different p-values here. If there's only a single predictor variable, the two p-values will always be the same. Well, I guess I should clarify. There's a p-value next to the intercept, which in most situations you can ignore. Then there's a p-value next to speed, which says 1.49 times 10 to the minus 2. Then down at the very bottom next to the F statistic, there's another p-value that says 1.49 times 10 to the minus 2. That's the p-value that we care about here. It's the p-value for testing the null hypothesis that p1 is equal to 0. You can see in this case there's very strong evidence against that null hypothesis. I'll explain the differences between the p-value next to speed and the p-value next to f statistic in a future lecture. For the time being, when you're doing regression on only a single variable, those two p-values will always be the same, so you don't need to worry about it. And you can get confidence intervals for regression coefficients using the command confint in R. If I say confint cars.lm, it gives me a 95% confidence intervals for the intercept and the slope. So we're 95% confident that the true value of the slope for this regression line is somewhere between about 3.1 and 4.8. In general, if you say confint of an LM object, that'll calculate a 95% confidence interval for the regression coefficients, and you can add the parameter level if you want a 99% confidence interval or some other confidence level. In practice, you almost always use 95%, which is the default. Let's say we want to make inferences about regression prediction. Let's say that for a given value of the predictor variable y, we predict the value, or for a given value of the predictor variable x, we predict the response variable y. We want to know how confident we are in this prediction. Here we have to explain something that's mildly confusing. It took me a while to understand, so don't feel bad if it's not obvious to you either. But in the previous lecture we talked about how you could predict the stopping distance when the speed is 21. There's two ways you can view these predictions, which correspond to two types of confidence intervals. That one way you can approach the question is if you looked at all the cars in the country that, or at least all the cars in the sample, and drove every single one of these cars at 21 miles per hour and then slammed on the brakes in all of them. Some will take more distance to stop, some will take less, and you could take the average stopping distance across, or you could take the average stopping distance across all of these cars. Another way you could view that is, let's say you just take one car from the population, take it to 21 miles an hour, and slam on the brakes. Intuitively, you would expect the variability for a single car would be greater than the variability for the average across the entire population of cars. And we'll see that is in fact the case here in a second. And some terminology in the context of regression: if you choose an interval such that there's a 95% probability that it contains the mean stopping distance, you call that a confidence interval. If you choose an interval such that there's a 95% probability that it contains the stopping distance of one given car, you would call that a prediction interval. So how do you calculate these things? Regardless of whether you wish to calculate a confidence interval or prediction interval, the expected value is the same. You just plug in the value of x0 and predict y, as we would intuitively expect. The best prediction is just what you get when you plug x0 into the regression model. But the standard errors for confidence intervals and prediction intervals are different. Standard error for a confidence interval looks like that, and the standard error for the prediction interval is at the bottom. You can see these two expressions are identical, except that there's a 1 in the bottom that's not in the top. That means the standard error for the prediction interval will always be larger than the standard error for the confidence interval. Like I said, I'm never going to ask you to use this formula in this class. We'll always do this in R, but if you ever need this formula, there it is. And the command to do this in R is predict. If you'll recall, we used predict before, but we didn't specify that we wanted any type of confidence interval. If we just say predict with new data equals data.frame speed equals 21, then it would just give us the predicted stopping distance, which is 65 in this case. But if you wanted a confidence interval for that, you use the predict command and add the parameter interval equals confidence. That goes from about 58.6 to 71.4. If you want a prediction interval, then you add interval equals predict, and that goes from about 33.4 to 96.6. In general in R, if you say predict on an LM object with a given new date and then say interval equals confidence, that'll give you a 95% confidence interval for the predicted values of new data using the regression object. And if you want a prediction interval, then you just replace interval equals confidence with interval equals prediction. And you can also add the parameter level equals 0.99 or whatever if you wanted 99% confidence intervals rather than 95%. As I said, in practice, you'll almost always want 95%. If you don't specify new data, then it will calculate the interval for each of the original x's. Another variable or statistic of interest when considering regression models is a statistic called R-squared, which measures the association between x and y. It's formally defined by this expression here, that the motivation behind this is the numerator of that fraction you can think of as the explained error. That's the errors that you cannot explain by the regression line, the yi minus yi hat squared. The difference between yi and yi hat would be 0 if the model was perfect. If that's imperfect, then there are some errors. The bottom is the errors that you would get if you had no information whatsoever about y, in which case you would estimate every possible value of y to be its mean y bar. So if this fraction is small, that implies that you can't predict very well without x, but you can predict very well when you do have x. If the fraction's close to 1, that would imply that having x gives you almost no information about y, so r-squared would be close to 0 in that case. And if you work out the algebra, I'm not going to torture you with it, but in the case of simple linear regression, R-squared just turns out to be the square of the correlation coefficient that I described a few lectures ago. So the way you interpret R-squared is R-squared will measure the amount of variability in y that can be explained by variability in x under the regression model. For example, if R-squared equals 0.75, then 75% of the variability in y can be explained by variability in x. R-squared can automatically be calculated by the summary command in R. That if you look down at the bottom, you see this multiple R-squared 0.6511. Means the R-squared is about 0.65, meaning in the car's example, 65% of the variability in stopping distance can be explained by variability in the speed of the car. A couple notes on R-squared is that R-squared only measures the variance in y explained by x under the assumption that the model is true. For example, if the true association between x and y is nonlinear, even if there is a perfect one-to-one association, say y equals x squared or something like that, if you had that model correct, you could predict y with perfect accuracy, but if we try to fit a linear model to y equals x squared, we'll get an r-squared less than 1. And the value of r-squared that's considered to be high would be extremely context dependent. If you can predict what direction the stock market is going to go in the next 3 months with an r-squared of like 0.05, then you can either publish your model and win a Nobel Prize in economics, or not publish your model and set up your own hedge fund and earn millions of dollars. In that case, if you're predicting better than chance at all, you're going to do extremely well. On the other hand, if you're converting Celsius into Fahrenheit, anything less than 100% would be considered unacceptably low. So you can't really say what's a high value of R squared in general. Also briefly note that it's possible to do regression through the origin, which is if you have an a priori reason to believe the value of y will be 0 and the value of x will be 0. The car's example is a situation where you might want to do this. If a car is moving at 0 miles per hour, it's reasonable to think the stopping distance will be 0 feet. And in fact, if you recall from the previous lecture, the predicted stopping distances by our model were negative for some of the values close to 0, which is kind of bizarre. We might think, that doesn't make any sense. I'm going to force the predicted value of y to be 0 when x is 0. And the way you would do this, you would force the y-intercept of the model that we've denoted by b0 to be 0 in our regression model. And the syntax for doing this in R is the following. That you use the lm command, again I say dist twiddle speed, but then I say -1. That's the only difference from the other regression model. And the command says, in general, if you say lmy twiddle x -1, that'll tell R to fit a regression model with no intercept term. If you fit a no-intercept model, you have to be very careful about your inferences. That if you use ordinary linear regression with an intercept term, the null hypothesis is there is no relationship between x and y, and the best approximation for y is that you let y equals y bar. If you do include an intercept, then the null hypothesis assumes the best approximation for y is that y equals 0 for all possible values of x, rather than y equals y bar. If you didn't follow that, don't worry about it, but the point of this discussion is that if you do regression through the origin, unless you want a null hypothesis that every single value of y is equal to 0, which in the vast majority of cases you know is false, you'll get wildly inflated R-squared and p-values, and the corresponding confidence intervals will be meaningless as well. So my personal opinion is that you almost never want to do regression through the origin. Maybe if all you care about is predictions, but usually when you do your regression, you're less interested in doing predictions than you are in identifying trends. And if your R-squared and p-values are meaningless, there's not much point in doing regression. And general caveats about assumptions for regression models is that, like any other statistical test, regression makes certain assumptions that if you perform t-tests or other statistical tests, like I said earlier, with the t-test we assume the data is a random sample from the population, the observations are independent, and if the sample size is small, we assume that it's approximately normally distributed. If these assumptions are violated, our inferences may be invalid. And regression also makes certain assumptions, and unfortunately, in practice, these assumptions are quite frequently violated, and it's important to know what will happen when these assumptions are violated. And unfortunately, that's a sufficiently complicated topic that I decided not to go into it in this version of the class. I can send you some slides from an old version of this class that talks about it if you're curious, or I'm happy to talk to you about it. But suffice it to say that you can get incorrect results from regression if some of your assumptions are not satisfied. Well, things to remember for today is that you can calculate the sampling distribution for regression coefficients and regression prediction, make inferences about these values using the appropriate R commands, and you can require that a regression line pass through the origin by doing no intercept regression, although in practice I usually advise against it. The new R commands today is you can use confident to get confidence interval for regression coefficients, and you can also use the predict command to calculate confidence intervals or prediction intervals for the fitted values for a regression model.